Welcome, everyone. My name is Aaron Smith with the Energy and Environmental Building Alliance, and I'm joined as always by Nancy Bakeman, and always excited to talk about ventilation. I've got the tattoo that says "Build tight and ventilate right." I think my last project I did was a 0.58 ACH 50, so trying to practice what I preach on what we do. But we're always happy to have Rowan Newton join us, and this will be cutting edge ventilation to improve indoor air quality, even with tight air sealing. So I'm joined today by a couple of great friends from Brown Newton, Patrick Nielsen, the Global Technical Products Manager for Brown Newton, and Travis Roche, the Group Product Manager for Fresh Air Systems at Brown Newton. And we will do standard today. You can put your questions in the Q&A section, and I will ask those to our guest panelists today as we go through, or we'll have some time for questions at the end. As always, this will be recorded and available at iba.org under our learning management system under the education tab, and also at the Better Homes, Better Future podcast. So Patrick and Travis, great to have you here.
Thanks. Great to be here. Okay, well, I'm going to start it out. I'll kind of cover some ventilation basics to get the ball rolling, and then second half, Travis will get into more detail on whole house ventilation systems and what some of your best options are there, especially with H and ERVs. So, what are learning objectives today? Why are homes with today's lifestyles more problematic for IAQ? What are the best ways to go about selecting good ventilation and optimizing its performance in the field? Again, H and ERVs, how they work, why are they so efficient, some tips on ventilation installation options, and then monitoring automation is probably the way of the future. So today's homes are tighter than ever. No surprise there. New energy codes, you have IACC 2021 adopted by quite a few states now. 2024 is coming. The requirements for tighter air sealing just get more and more. As Aaron mentioned, build tight, ventilate right, never been more true. So, the pandemic, obviously a terrible thing, but really helped to raise people's awareness of indoor air quality. And we're still seeing that in the growth of IAQ monitor sales. That's a definite signal that homeowners, people in general, are concerned about the air they're breathing. And we're really seeing builders, like yourselves, energy efficient builders, we're really thinking about their health messaging as well. Not just, we're going to build you an efficient home, but a healthy home as well. So we're obviously making homes much tighter. We have new technologies out there like aero barrier. Essentially, you can get a home as tight as you want. Better doors and windows, obviously. When we talk about blower door scores, to show how far we've come, back in the 70s, the average score was, 12 plus. It's hard to imagine today any new home built being anywhere near that leaky. But today with the new energy codes, we're averaging low single digits. So great thing again for energy efficiency, but now we have to make sure people have fresh air as well. So one of the obvious things I think a lot of people don't think about, why is it more challenging, is we just don't open windows as often as we used to. Now that almost everyone has central AC, so we use our thermostat to control our comfort level, not opening and closing windows anymore. So you don't get that nice natural fresh air. What types of pollutants are we concerned about indoors? There's a number of them. One big one, if you haven't heard of it, is called PM 2.5, which stands for particulate matter 2.5 microns and smaller. You'll also may have heard PM1, PM10, so on. 2.5 is getting a lot of attention because that's the size where it can start going through our nose, through our lungs, and into our bloodstream. Obviously not something we want to have happen. So other pollutants, gases and VOCs, paints, carpeting, all these things are off-gassing, things like that we have to worry about, formaldehyde and so on. Excess moisture, I think a lot of people don't think of that as a pollutant. But when you think of, a lot of the bacteria and viruses and so on, they really thrive in high humidity environments. So we really need to control humidity in order to control other things. And obviously, mold and mildew, people don't want that, growing in their grout and so on. And then obviously odors. I think for a lot of people, odors is their trigger. They think if my house smells bad, I must have bad IAQ. Um, you talk to people who go into homes IAQ specialists, and that's what they say. We get the calls when people think their house smells bad. So in the upper left image here, I'm showing a gas range top. That's really getting a lot of attention. A lot of research being done on cooking and all the effluents that come from that. But gas cooking is especially bad compared to electric. Whenever you're burning fossil fuels, you have to worry about carbon dioxide, carbon monoxide, nitrogen dioxide, all these other things. So a good quality range hood is very important. And for anything that the range hood doesn't catch, again, whole home ventilation is the answer. I mentioned PM 2.5. It's everywhere, comes a lot from cooking also. But one thing we like to assume that outdoor air is fresh air. But with all the wildfires we've had the last 5-10 years, outdoor air isn't always fresh air. So as evidence of that, as an example, California now requires MERV 13 filtration, which is going to catch almost all that PM 2.5 from wildfires. They require that on any incoming air. So if you have a supply fan system or HRV with incoming air, you need MERV 13 filtration on that. So something to keep in mind that may be a trend that's going to sweep across the country. And I know ASHRAE 62.2 is talking about increasing filtration requirements as well. So what happens? We tighten the envelope. Obviously, a good thing. We're going to lower the sensible loads. Going to make our home less expensive to heat and cool, but we're also going to increase the latent loads. All that shower and cooking humidity has no place to go now, so we have to think about that. So that can result in the shoulder seasons when it's not warm enough yet for the AC to run. Of course, your AC does two things for you. It cools, but it also dehumidifies. So if it's not having to run to cool, it's also not dehumidifying. So you can get, very uncomfortable conditions in certain times of year. Another aspect we want to think about is depressurizing dwellings. So this can be a concern if you build a very tight dwelling, which we want to do, of course. And then if you run, a very high CFM range hood, or you're running your range hood and your dryer that's pulling out 250 CFM, we could potentially backdraft things like gas hot water heaters. We don't want carbon monoxide coming back into the room, of course. So something to think about. It could also pull in radon from under your subslab, could pull in pollutants like gas or whatever you're storing in your garage, leftover exhaust fumes from your car. So, think about really tight homes. You don't want a lot of exhaust devices running at the same time. So I'm going to switch gears a little bit and talk about some ventilation basics. For any of you that are relatively new to ventilation, one very important organization is HVI, the Home Ventilating Institute. Great if you get a few minutes to go to their website, hvi.org. HVI is both the certification body. So when you see that a bath fan or range hood or ERV is HVI certified, you can trust that the CFM level, the sound level, the wattage, the SRE, you can trust those numbers. And it's also a trade organization. So on their website, they have something called their certified products directory. The bottom half of the slide, you kind of see a sample there. You can sort by manufacturer, by type of ventilation product, and you can see any certified model, what's its airflow at different static pressures, what's its sound level, wattage, again, SRE in the case of H and ERVs, great resource to get information. I want to touch a little bit on zones here as well, because we get a lot of questions on zones. What is a zone? Obviously, it's a measure of sound. The reason the industry doesn't use decibels is because they're on a logarithmic scale, and a lot of people can't wrap their head around a logarithmic scale. With zones, it's linear. 2 zones sounds to the human ear twice as loud as 1 zone. If you ever see, this is important, if you ever see a measurement like on a bath fan of less than 0.3 zones, that's the quietest rating you can get. They've determined that 0.1 or 0.2 zones, the human ear can't even hear that. So if you're looking for the quietest products you can get, you want to be under 1 zone for sure. Less than 0.3 is the best you can get. Another common question we get is, well, how loud is a zone? The common equivalence, I guess. 1 zone is like a quiet refrigerator running. If you're home alone and you hear refrigerator kick on, you can hear it, but it's not objectionable compared to a 4 zone. That's your typical economy bath fan, which most people uh, tend to complain about. So static pressure is very important. If you have background in HVAC, you're probably familiar with duct static pressure, but for those who aren't, it's an extremely important concept. So static pressure is a measure of resistance to airflow. So as your bath fan or ERV is trying to push exhaust gases out of your home or pull them in the case of an ERV, you want that duct run to be as short and straight as possible, low static pressure, so that ventilation device can do its job efficiently. So this graph you see here is a graph of a typical 80 CFM bath fan. So on the vertical axis, we have static pressure, and then horizontal axis airflow. So if you look at the blue horizontal line, that's at a 1/10 inch of static pressure. That's a very, very good level, a good duct installation. So I draw a blue line there because for bath fans and range hoods, that's the standard rating point. So if you pull that across, go to the red fan curve of this fan, drop it down, you'll see why it's rated at 80 CFM. At a 1/10 inch, it'll move 80. But more commonly, if you look at the black lines, the codes are starting to say a 1/10 inch is unrealistically low. If we went out there and looked at 1,000 bath fan installations, 900 plus of them would be well over a 1/10 inch. So the codes are starting to say, don't look at the 1/10 inch rating, look at the 1/4 inch rating. So you can see in this case, this bath fan only moves 60 CFM. So very important to understand. So you want to minimize static pressure, keep diameter of your ducting at least as great as the duct connector on the device, and keep your runs as short and straight as possible. And if possible, use rigid ducting rather than flex. So as evidence of why this is important, all of the residential codes, IRC since 2015, have this duct sizing chart. So if you can see this table at the bottom, in the upper left-hand corner of that table, it says to use the fan airflow rating at a 1/4 inch of static pressure. So again, you should go to the product spec sheet or go to that HVI certified products directory and find that level. So it's very important here in the example of a bath fan where you need to move 50 CFM per code. If you can see in that first column, flex duct 50 CFM, 3-inch diameter, there's an X there. That means it's not allowed. You're never going to move 50 CFM with a 3-inch ducted product, is what the code is saying. You have to move to at least 4-inch ducting, and there you're allowed 56 CFM. Now, it's noteworthy this table has the termination fitting, a roofer wall cap baked into the numbers, but it does not bake in elbows. So you have to subtract 15 feet for every elbow from the numbers you find in this table. Where you see NL, for instance, at 5-6-inch ducting, that means no limit. You can have as much ducting as you want. So this is probably the most common way that inspectors or HERS raters are checking for field verification of airflow. They're going to check the box based on this table, but they also can do a field verification test, as you see in the image in the upper right here, a HERS rater inspector checking it with an actual device, or you can comply with manufacturer's criteria. That's your third option. So I'm going to step back a little bit and talk about ASHRAE 62.2. You probably heard this a million times in your life, ASHRAE 62.2. It's important. Some people confuse and think it's a code. It's not a code, it's a standard. So ASHRAE is the American Society of Heating, Refrigeration, and Air Conditioning Engineers. They do a lot of research, and they decided this is a minimum amount of ventilation for good residential air quality. So it's updated every 3 years. They just put out the 2022 recently. 2025 will be coming soon. But it's noteworthy. I still show 2010 in this first bullet. because when it comes to whole home ventilation requirements, the CFM levels in the building codes are still based on the 2010 version of ASHRAE 62.2. I'll talk a little bit more about that going forward. There's a handful of states, such as California, that directly reference some of the more recent versions, which call for greater CFM. I think the reason the I codes are going with the old version is because it's much simpler. All you need to know is number of bedrooms and square footage, and you can calculate your airflow. So ASHRAE 62.2, obviously there's two basic types of ventilation. There's local or spot ventilation. We take a shower in the bathroom. We want to get that humidity out while it's trapped in that room at that point in time. We're cooking. We want a good range hood to catch those pollutants while we have them there in that room at that point in time. This is called local or spot ventilation. So ASHRAE 62.2 says for bathrooms, after your fan's all said and done installed, you need to be moving at least 50. Of course, more is better all the time. And the equivalent with kitchens, you need to be moving 100 CFM ducted exhaust ventilation. What we'll probably spend most of the rest of the time in this session talking about is the concept of dwelling unit ventilation. You'll also hear whole home ventilation, the acronym DUV. So this is saying even if you do a great job with that local ventilation in the bathroom and kitchen, you're still you want some turnover. We constantly want to be getting some stale air out and some fresh air in, 24/7, 365. A little bit of a side note, one of the requirements in ASHRAE is also regarding sound. They say for local exhaust, that bath fan or kitchen range should be a maximum of 3 zones. And for dwelling unit ventilation, if you're going to use a bath fan that's running 24 hours a day, that should be less than 1 zone. The reason they're concerned about this, obviously, if people find the noise objectionable, they're going to turn off the device and then you have no airflow at all. But as I note in the last bullet here, these requirements do not carry over into the I codes. So there's nothing in the IRC or IMC regarding zone limitations, but obviously it's still a good practice. As builders out there in the audience, firsthand, you don't want callbacks, and that's a very simple callback to avoid that ventilation's too loud. I mentioned earlier how we don't want to depressurize buildings. The key thing when it comes to this in codes is what they call kitchen makeup air. So the IRC says if your range hood is greater than 400 CFM, you need makeup air. So the image here kind of shows a typical makeup air damper. So what this is going to be, you're just going to have an inlet on the outside of your home. Let's say this is a 6-inch diameter inlet. Run through this motorized damper and typically just into your return air existing HVAC plenum. You'll see it has a little motor on the top. So this is tied into, usually with a low voltage line, tied into your range hood. So when you turn your range hood on, it says and signal to this to open up. So as your range hood is pulling air out of your tight home, potentially depressurizing it, this will let makeup air come in and kind of rebalance that. So you don't have to worry again about your, gas hot water heater backdrafting, your natural wood burning fireplace backdrafting, things like that. Different states alter that 400, but that's the general rule. So here again, we're going to switch gears and talk about dwelling unit ventilation, whole home continuous ventilation. So in the ever since the 2012 model codes, this is where the energy code started requiring it. So again, this is based on ASHRAE, the 2010 level. So as ASHRAE was determining how much fresh air do people need, they came up with the formula 1% of square footage plus 7.5 CFM per person. So to estimate the number of people in a home, they use number of bedrooms plus 1. The proxy being, bedrooms probably each have 1 person, but the master bedroom probably has 2. Your typical 3-bedroom home probably has 4 people, parents and a couple kids. So in an example, 2,500 square foot 3-bedroom home, 1% of 2,500 is 25 CFM for that half of the equation. And then 7.5 times 4 is 30. Add those together. This home needs 55 CFM. Should constantly be pushing 55 CFM out, bad air, and pulling in 55 CFM of good fresh air. If you don't like even that formula, the code also has the table on the right, which gets you to the same place, just in table form. So 2021 I code changes. This has probably been adopted by about 10 or 12 states now. One very important thing is they require that you field verify your dwelling unit ventilation airflows now. So very important to make sure you're putting in a ventilation device that's going to get the job done for the requirements, and that you duct it properly. Keep the static pressure low enough so when that HERS rater comes and checks, you can be comfortable that you're not going to get red tagged. So with each energy code update, and I should mention the 2024 codes are out there now. So next year, 2025, we'll start to see states adopt that, and that has even more stringent energy requirements. But ERVs are now required in single family climate zone 7 and 8. When it comes to the 2024 version that just was put out there, they're going to add climate zone 6 to that. So ERV requirements keep working their way south from the most northern climate zones. They're realizing, more and more often that they're going to pay themselves back with good, efficient, fresh air. And on the multifamily side, if any of you are involved in multifamily, for 4+ story high rise, prescriptive path now requires ERVs. So again, with each passing year, the codes are more and more requiring or incentivizing ERVs. So how do we achieve fresh air? At this point, I'll turn it over to Travis. The 3 basic ways. You can do exhaust only. We're gonna, run a bath fan 24 hours a day, suck out the stale air. Negative pressurization, fresh air will make its way in, is option 1. Option 2 is supply. We'll do just the opposite. Let's push that 55 CFM in our example home fresh air in. We'll pressurize the building. The stale air will get pushed out of the nooks and crannies left. And then, as Travis will allude to, balance is your best option. We don't have to worry about holes in the building envelope. We're going to mechanically do both pieces, and ideally with recovery. So Travis, take it away.
All right. Yeah, thanks, Pat. So as Pat mentioned, the 3 approaches, and we'll spend just a short bit of time on the exhaust strategy. So again, we're having a dedicated exhaust fan. Typically, like Pat mentioned, has some requirements as relates to zones, as well as the CFM that's being delivered. Again, this is typically put in a place and or can be piggybacked on another bath fan within the house. But again, it has its job is for the whole home mechanical ventilation. And you can see here there are some different options as relates to models and various features in which you can include with this type of product, being both humidity as well as like a timer control, as well as CFM. So as Pat mentioned, you have that table, you have that calculation that's being done. These particular models can offer that full range so that you can dial in that CFM that you're requiring based on that calculation or that table that Pat had shown earlier. The next approach is that supply. So this is where we have a dedicated duct that runs from the outside to the inside of the home, passing through this type of product. So we have a known source of air, fresh air. In most cases, we're going to filter it, whether it's with like a damper going through your return side filter, or in the case of like a supply fan where there's dedicated filtration within the product itself. So again, a known source of fresh air. We're going to positively pressurize that envelope by using this supply strategy. And finally, there's another approach, which is the balance approach. And so this is taking those 2 products and making them work together. So if we have an exhaust fan set at 55 CFM and we've got our supply fan set at 55 CFM, we're basically neutralizing that pressure within the building, taking a balanced approach. Again, this is not having any recovery related to this approach. This is something that's used in those much more mild climate zones. Think like San Diego, California, or areas in the country which, again, the outside air and the inside air typically aren't that much different. Kind of the best solution, and Pat kind of alluded to it, is that balance approach with the recovery. And so we're going to touch on 2 main types and dive a little bit more into the details of these types of products. So when it comes to an HRV or ERV, there's really 3 key components that these products feature. And the first is a filter. So we're bringing outdoor air in, and you saw some of the different images previously with the wildfires. Just we could have high pollen season, etc. The first part is that filter. So it's the first line of defense for that outdoor air that's coming in. Once we get that outdoor air in, we're going to use blower fan motors. So basically, we got to draw that air in from the outside. We've got to draw that air from the inside of the building and make sure that we're moving those airflows consistently and in the same CFM. And what happens is these airflows pass through what's called a recovery core. So that's that cube-shaped thing you see in the middle there. That is our recovery core. And what's going on inside our recovery core is you're going to see there's thousands of these little air channels. And within each of these air channels, if we do a cross section there, let's say it's a cold day outside, we've got our house being warmed up. We've got that cold air coming in through the one side of the channel. There are alternating membranes essentially. And so the air paths themselves don't touch, but instead what we're doing is using simple thermodynamics to let the cold air in this case be warmed up by the stale air we're moving from the building. So hot goes to cold and wet goes to dry. And so we're utilizing this fairly simple technology to temper the air that we're bringing in from the outside, while in the same fashion pulling that stale polluted air from the dwelling in the same rate. And so again, you can see how we're utilizing those air channels and ultimately that membrane, which allows that transfer to occur, that exchange to occur from that fresh outdoor air, from that stale indoor air that we're pulling from the dwelling. And there's two types when it comes to these recovery ventilators. And the first is HRV. This is a technology that's been around since the late 70s, early 80s. Started up in Saskatchewan, Canada, has since obviously proliferated. We're using them, have been using them for quite some time now throughout the North American market. With an HRV or heat recovery ventilator, we're simply moving a sensible transfer. So temperature, hot going to cold. So as you see in that upper right cross section there, again, we've got cold air coming in. We've got that stale polluted air getting pulled from the house that's warmer. We're going to warm up that outdoor air in this situation with an HRV. The other is an ERV or energy recovery ventilator. And honestly, over the last few years and probably over the last decade or so, we've seen a significant shift from that HRV to the ERV technology. And really the key to this is not only do you get the same sensible transfer, but you're also getting a latent transfer or moisture vapor. So we're kind of getting the best of both worlds. We're getting that sensible transfer we got from the HRV, but also we're adding this latent component to it. And to be honest too, the cost of these two products has got much more in line than it had been maybe in the last 5 to 10 years. So the popularity of ERV has jumped up significantly. And again, it's because you're getting the benefits of both temperature and moisture vapor transfer with these two technologies. When it comes to the climate zones in which we're handling with these types of products, I often get asked the question, hey, what's best in my climate zone? Is it an HRV? Is it an ERV? And to be very honest, particularly throughout at least the lower 49, I'll say, including Hawaii, ERVs are pretty much becoming more and more prevalent. A big part of the reason for that is the technology itself, the materials in which we make those recovery cores out of, our ability to defrost that recovery core, particularly in those very cold conditions. So again, if a ERV is going to retain some amount of that latent, and we've got condensation developing within that recovery core, the last thing we want to do is when we bring that fresh air in, is turn that recovery core into an ice cube. And so through the technologies we've got within that recovery core, that membrane or that material in which it's made out of, as well as our ability to more effectively defrost or basically maintain the recovery core from frosting, we were able to take that ERV technology and honestly move it all the way up, certainly into climate zone 6, and you might even get into part climate zone 7 as well. There are different versions of ERVs that are more, I'll say, compatible for those colder climates as well. But again, we do see more and more ERVs being used throughout all these climate zones shown on this map here. We do still have some diehards, particularly in the Minnesota market, using HRVs. God bless them. That's perfectly fine. But you're going to see a continuation of ERVs growing more and more popularity. And again, main component being that latent transfer that you get with an ERV. So giving you some real world examples of what's going on here. If we look at like a cooling season, so let's pretend we're in Phoenix, Arizona. It's 110 degrees outside. I've cooled my house down to 75 degrees. What we're going to do is we're going to take that difference in that outdoor air, in that indoor air, and we're going to recover a certain percentage of that. So as you can see in this example, we're using that 75-degree stale air from our house to cool down that incoming outdoor air at 110. So by simply moving this air through that recovery core that we talked about earlier, we're able to take that 110-degree air and temper it down to 83 degrees in this example. And again, that's just the percentage of the delta or the difference between that outdoor air and that indoor air to determine what are we going to deliver to the home after it passes through this product. Same can be said for a heating season. So we're in Minneapolis, Minnesota. It's negative 13 degrees Fahrenheit out during the winter months. We're warm in our house. The family likes it nice and hot, 75-degree Fahrenheit. And we're going to take that negative 13-degree air and warm that up to 61 degrees just by passing this type of product. And so you can see, again, you saw how simplistic, there's no really moving components inside these outside of highly efficient, durable blower fan motors. We're taking these air paths and making them do some work with one another. And so, again, you can see the greater the difference between that outdoor air and that indoor air, the more efficient these essentially become in our ability to deliver that much more tempered air from what would be outdoor air conditions if we weren't doing any recovery with them. We'll also go hit on the humidity management. So we've got a very humid climate. We've got a high dew point, high relative humidity. We've got that moisture coming in from that outdoor conditions. So let's say we're in Orlando, Florida, as an example. Our air conditioner, or maybe we got supplemental dehumidifications, doing a good job of maintaining our indoor dew point and relative humidity. Again, wet goes to dry. So we've got that moist air coming in from the outside. We've got that dry conditioned air from our inside. That moisture is going to make its way. Again, that transfer is going to happen within that recovery core. We're going to remove a certain amount of that humidity from that incoming airstream. So if we were to do nothing with it, we'd have that raw humid air coming in. Now with the use of an ERV, we're going to be able to use that stale polluted air, that conditioned air from the inside of our homes to condition it. I will stress these ERVs, they are not dehumidifiers. So we are still going to be delivering a certain amount of latent after the ERV. So again, these are not dehumidifiers, but they do a nice job of removing a certain amount of that latent that would be incoming to our homes had we not had this type of product. The opposite could be said too. So let's say we're back in Phoenix, Arizona, dry climate, very low dew point, very low relative humidity out there. We've conditioned our house, again, whether it's an air conditioner, or maybe we've added a humidifier to our homes, and we're adding humidity to the inside of our homes. Again, wet goes to dry. The recovery core really doesn't care which side is which. It's just going to simply move wet to dry or hot to cold on each side of that recovery core. And so the same thing happens. Instead of having that moisture get basically displaced out, we're actually going to recuperate some amount of that moisture and bring it back into our home. So again, ERVs may be thought of in those more humid climates, but honestly, they also provide a benefit in those drier climates by retaining some of that moisture and reintroducing it back into the home, in which, again, you're either adding that moisture, whether it's your air conditioning system or humidifier, you're adding moisture for some reason, typically to keep your house more comfortable, keep your building materials integrity. And again, you're going to get that benefit of that moisture basically being reintroduced back into the house. Pat showed some of those images. We'll reuse those again. I talked about that kind of at the very beginning as relates to the key components of a HRV or ERV, and that first one being that filter. As you guys may be aware, there's a multitude of levels of filtration. What you're going to find in the industry, and we've certainly moved closer and closer, but you're going to start seeing MERV 8 kind of be the standard as it relates to the filtration. You can see the different particle matters in which these particular levels of filtration capture. And again, as you work your way towards MERV 13, ultimately HEPA, you're going to see how our efficiency or capture efficiency only increases, as well as our ability to capture that smaller particle matter that Pat had mentioned earlier in the discussion. So another big question we get is install. So we've got HRVs, ERVs, we understand now how they work, what are the key components, but how do we go about installing them? And so the first is what we call simplified installation. This is where we're going to use the home's existing HVAC ductwork. So if you have a forced air system, you've got that ductwork running to and from various areas of the home, we're going to leverage that. And so this is an example here with what we call a return to return, or essentially what we're doing is we're pulling stale air from the return system, and downstream or close to the air handler, we're introducing that fresh filtered air from the HRV or ERV within that ductwork. There's an alternative to this that you would introduce that fresh air from the HRERV into the supply side of the air handling system. And again, this would require some type of interaction with your air handling system and these units running, just to make sure we're getting the benefits of, leveraging that ductwork and having that air get distributed accordingly throughout the house. The next is what we call dedicated exhaust. And so just like the name states, we have dedicated duct or ductwork running to various areas of the home. Pat kind of hit on it earlier. Typically, our most polluted areas of the home are our bathrooms and our kitchen areas. Again, for the various reasons that Pat mentioned earlier on the pollutant side of things. So it's typical that you will have your stale air extraction from your home going back to the HRV or ERV, being pulled from those types of areas. And then in this case, we still have our fresh filtered air coming from our HRV or ERV and can either go into the return side of the air handling system or into the supply side to, again, leverage that ductwork that we've got for our forced air system. So a couple real world pictures there in the upper right. Again, you can see how this, in this case, the ERV being placed in the mechanical closet, being mounted to the wall there. And we've got our ductwork running into the return side of that air handling system. And then in the bottom left picture, we have a bathroom, and actually the register grill that's closest to the end here is what's actually being the stale air extracted from that bathroom. And in the case here, there is what we call a boost switch or override switch that would wire back, low voltage wire back to the HRV or ERV, and you can push that switch to basically boost that HRV or ERV to its maximum speed setting, which again, maybe you have it running at a low continuous number, and then you hit that boost switch and it'll take that unit up to its maximum CFM setting, ultimately try to extract that humidity, that odor, etc., out of that bathroom as quickly as possible, and ultimately be a replacement for a typical bath fan in this type of situation. Becoming more and more common practice. See a lot of this being done, particularly in that multifamily side of things where floor space is a premium, exterior ductwork terminations can become a problem as well. I'll share some different solutions we have with those as well. But again, I'm seeing this being done more and more for the various reasons and the simplicity that can add to the overall design of the building. The final is a fully ducted install. So again, just like the name states, we've got dedicated ductwork running to both on the supply side as well as exhaust side. So same principle as talked about before, that stale air being extracted from those mainly polluted areas of our home, being our bathrooms and our kitchen areas. Certainly could run it to other areas as well. And then your fresh air being distributed to the main living areas. So the bedrooms, the living rooms, etc. Again, leveraging dedicated ductwork to truly get that air exactly where you want it to go and not relying on the ductwork maybe you have from your forced air system. Also very handy if you're using like ductless mini split heads or baseboard heat, etc., where you don't have the opportunity to leverage any kind of ductwork. Again, you have dedicated ductwork running to and from the HRV or ERV. And again, seeing it very similarly utilized as a bathroom fan extraction point in place of a bath fan, like shown in the lower right picture there. And again, you can see how this ductwork can get fairly complex, or again, if you really want to pull from all those different areas and supply to all those different areas, making sure you're accounting for that in your floor plan designs and making sure you have adequate space to ductwork to run to and from. I alluded it to before, as it relates to exterior terminations. Again, we've got to bring fresh air in from the outside to feed that HRERV And we've also got to take that stale air from that product and take it back to the outside. And there are a couple different approaches to this. You could use two separate independent sets of terminations, again, having their corresponding need, or you could utilize what we call our tandem or concentric terminations shown here on this slide. So you have like a vertical stack, I'll say, so the exhaust air from the H or ERV is going to go out the top side of the product, and then we're going to draw that fresh air in from the bottom side, and you can see in that cross section there how we're splitting those two airflows to make sure there's limited amount of contamination. In the case of both of these, that percentage is less than 5 or even less than 3 in the upper one. Again, we want to make sure if we're going to be pulling fresh air in from the outside, not that we're reintroducing the stale air that we just took from the inside back into it. So between the design of these types of products, the consistent velocity in which the airflows are entering and exiting, all play a factor into how we can make sure that these are limiting the contamination within it. And again, these would feed to and from HRV or ERV in these configurations. Pat did hit on HVI, just again stressing the importance of HVI as it relates to if a product's not listed within the HVI directory that Pat showed earlier, doesn't mean it's certified. And so why that matters and what you're going to see as you dive deeper into the codes, and particularly the 2021 code, is you're going to see there's certain, in this case, fan efficacy requirements related to these whole dwelling mechanical ventilation systems. So you can see here the note or the verbiage that's highlighted. Fans shall be tested in accordance with HVI 916 and listed. So you're going to see here how there's a direct correlation between what HVI does and their certification process and the need for the product itself to be on that certified directory or listed on that certified directory. So look for logos, look for that HVI logo, whether it's on the spec sheet, the product itself. There's certain requirements on where that logo is present on products, just to ensure that, when you're specifying or when you're physically installing those products or making that buying decision for your building, that you're doing that with an HVI certified product, because it is like Pat mentioned earlier, it's a body in which that keeps all of us as manufacturers honest and making sure that when we provide a product to market, that it does exactly what we say it does. And again, you can see code has recognized that importance and it is implementing that type of language in these types of code verbiage going forward. Kind of one final note, and Pat mentioned earlier, on what are we doing to be more active related to indoor air conditions? The days of relying on the dwelling occupant, the homeowner, activating their kitchen range hood. I'm guilty of it. My wife does not like the sound of our range. Very old model, does not like the sound of it. So for that reason, she doesn't use it often. And so we're often fighting that. I would love for her to use it all the time, but the reality is it's too noisy, so she doesn't use it. So how do we kind of get around that? Same thing for bath fans. Very common, particularly if you have kids in those teenage years, taking those longer showers, either forgetting or just not turning on that bath fan as an example, and you go in there and the mirror's all fogged up, you got humidity, just beyond belief in that room. That's where we can take this active approach. And there are a number of systems out there, including our Overture system, which takes that, basically takes that variable out of it and is going to utilize a number of sensors to detect those pollutants and then do something about it. So in the kitchen and range example, we could use that wall switch or that sensor that we've got to detect when those pollutants become over a certain threshold and activate our range hood, or the same thing with our exhaust fan, activate that exhaust fan, or if you have it hooked up to a H or ERV. When you have those types of conditions, let's do something about it. Let's introduce that fresh filtered air to dilute some of those pollutants that we may have going. And with this type of system, you can actively determine, based on the sensors in which you've installed in your home, what are the pollutants that, based on the pollutants, based on their content, what is it you want it to do? Maybe you just want the bath fan to turn on because that's where your sensor is in your bathroom for humidity, or maybe you want your kitchen range hood to turn on when the PM 2.5 gets too high. those are the types of things, those are decisions in which you can make all through a simple app on connecting your ventilation system, managing indoor air quality without any kind of intervention as a homeowner. And again, that's peace of mind for, again, whether it's yourself as a contractor, builder, etc. We're taking that variability out of it and ultimately providing a better experience for that homeowner and ultimately a better quality of life in the bigger picture of things. So we've got the active portion, we've got the physical hardware of the sensors in the home. We're managing it through an app, but the kind of the final piece is too, is as Pat showed earlier, there are times of the year where our outdoor air conditions aren't ideal. And so how do we work all this together? And that's where you can get that next piece. And what the system does is monitor outdoor air conditions to determine, hey, this might not be a good time to be bringing fresh air in through my supply fan or my ERV. So utilizing outdoor air quality APIs and interconnecting those to make those better decisions on when is the right time to introduce that fresh air based on, real-time measurements being taken with that outdoor air quality. So that's kind of where we're at as it relates to kind of what the future looks like. And again, these types of products are out there already. This type of technology is out there. Again, really to help bring everything back together as it relates to managing indoor air quality and ultimately lending itself to a better quality of life. So with that, are there any questions? Anything in the Q&A? Does not look like it.
Yeah, I don't see anything right now. I've got a couple of questions that came to mind. Now I'm going to give a Minneapolis example, but I feel like we all know that, under Energy Star and zero energy ready homes, we need to have ventilation at the range. Typically, we'd want under the 400 CFM. Typically, you'd want to specify an Energy Star hood, an HVI certification, and a low SONS level. Help me find, like, is it just that my local distributors in Minneapolis are not stocking the fine products from Brown-Newtone? What am I missing? Like, is it hard to get right now, or am I missing the mark?
Which piece of that are you having a hard time finding? The Energy Star or the Quiet or?
Well, I think basically at EBA, we've worked on, specifications for builders around the kitchen range hood in particular. So trying to hit all the hurdles of, hey, we want below this many zones but I would say the hardest one, Travis, is there seems to be, when you go to your local appliance store, you send your homeowners there, they're like, well, we don't know which one's Energy Star. Are you seeing that nationally, or is this just a Minneapolis thing?
One thing I'll say about Energy Star with range hoods, for a lot of years, there weren't many out there. And it
Yeah.
wasn't because of the ventilation efficiency, CFM per watt, is because you also have to meet the lighting
Right.
requirement.
Right.
And, most of the world had gone to LEDs, but LEDs traditionally can't handle the heat of being above a range.
Okay.
So it wasn't the ventilation problem, it was the lighting. But last
Okay.
year, they canceled all that out. So you don't have to worry about, and now they have better LEDs too that can withstand the heat of being above a range. But you're going to see a lot more Energy Star range hoods coming on the market now because they
Good.
don't have to worry about the lighting component.
Okay. And are we traditionally going to see Brown-Newtone range hoods offered through, I'm thinking of the big appliance shops, or is it more that we're going to pull those through our HVAC installer?
Yeah, they should be widely available,
Okay.
all those channels, Home Depot, Lowe's, a lot of them online. A lot of appliance outlets have online stores and so on. They should be pretty widely available again, especially Energy Star more so going forward.
Great news. Great news. Um, Travis had a question on the ERV versus HRV. I mean, you said there's some stubborn Minnesotans, but my take on it and what I've learned from both of you over the years is we should all be looking at ERVs unless you're in some sort of an extreme climate. What's holding people back from making that switch? Is it just education in the marketplace?
Yeah, and I think that's a big part of it. There was some I'll say stumbling blocks out of the gate as relates to ERVs. I think, again, this was many years ago, but I think there were some promises related to this thing's going to work regardless. I think that may not have actually been the case. The technology may not have been to that point. I talked about, the materials in which our recovery cores are made out of, how we're defrosting them. I don't think those were necessarily up to snuff. So I think some people had a bad taste in the mouth. Again, I use the Minnesotans. God bless them that they're doing what they're doing. But yeah, I think that's the reality. And like I said, I really think that's it. I mean, we've got ERVs being utilized in, Alaska, in many parts throughout Canada. Again, these have been either code or been very prevalent in Canada for going on probably close to 40 years now. It can certainly be a lot colder up that way than even we're in Wisconsin, you're in Minnesota, Aaron. I always joke our engineering team's closer to the polar bears than we are. And so they take that very seriously. The durability testing, which they do, is pretty extreme. So yeah, I think it's just an education piece. That's why it's important for these types of conversations, these types of education opportunities to get that message out there. Because you're right, you're gaining a bunch of benefits of having that ERV, even if you have, like, even here, we have those few weeks, I'll say, where it's truly quote unquote humid out. That's completely different than Houston, Texas. But I'm getting the benefits of having an ERV in my home for those periods of time. And again, we're getting the same sensible transfer. So it's not like we're giving up one to get the other. It's the reality is we're getting both. So yeah. Then, like you said, I think it's more education.
Patrick, what are you seeing on the code changes? I mean, I'm here in Minnesota. We've had ERV, HRVs as a mandatory part of our code for, I think we're going on 20 years now. It might be more than 20 years.
Yep.
And Canada also very similarly, ERVs, HRVs in the code. But I don't think any other of the 49 states have yet. Are you seeing any shift toward? Because my feeling is it should be mandatory. I mean, healthier homes are the next frontier. I think we realized that during COVID. So what are you seeing out there in kind of the legislation or mandating landscape? Are we going to see more ERVs, HRVs?
Yeah, definitely. Again, it's mostly related to the IECC, the energy code. They've been required in climate zone 7 and 8 in IECC 2021. And now in the 2024 version, they've added climate zone 6. And so we hope in the 27 version, we can add climate zone 5. So we keep bringing that down. Again, multifamily, 4+ story, they're required prescriptive path, which we understand is what most. And I think the other big driver we're seeing is the 45L tax credit. To get that, you have to hit Energy Star Homes version 3.2.
Right.
And to get 3.2 versus 3.1 version, you have to find 10 extra HERS points somewhere.
Yeah.
And we've done some simulations, and depending on your climate zone and so on, you can gain from 2 to 6 HERS points by adding an ERV. So we're really finding builders, maybe they're not required to put in, but really getting incentivized in ways like that.
That's fantastic. The 4-story and above ERV, HRV in multifamily also would require through Energy Star to have a ventilated hood. One of the things I think that we've talked about in the past is, do you have a wall-mounted ERV, HRV for multifamily? And then one of the other challenges in multifamily is, being 10 feet apart on your exterior penetration of the wall. So I think you have a boot intake outlet boot now. Can you just talk about those solutions, if they're upcoming or not? And hey, there's the boot. I've seen that one.
Yeah. So those determinations. So yeah, exactly. Taking that, not that issue, but that, again, having that requirement for that 10-foot separation. And again, we've obviously done our due diligence in testing these types of terminations previously. We provide that data to any of those jurisdictions. There's often a question like, hey, you got these two airstreams right next to each other. How is it possible that you're not drawing back in? Kind of go through that whole dog and pony show showing, hey, here's how we tested them. Exactly.
This is literally one when you run into an authority having jurisdiction that says this is a no-go, like, you got to get Travis on the phone, because he's got all the HVI and ICC, he's got all the testing data. And I think what the AHJs or building code officials really want is, oh yeah, this is tested. I'm going to put this in the file for the project, and this is an acceptable solution.
Yep, no, you're exactly right, Aaron. That's kind of the, like I said, kind of the ticket to have is just having that conversation. I know we're working from a code standpoint to kind of alleviate that trouble is get that code language to recognize that, if this is a termination that comes from a manufacturer of this type of product, that again, we've done our due diligence, tested it, et cetera, that it's an acceptable means versus right now we're kind of in this we're a bit of a speed bump where they see this, it's a great solution, but you're right, Aaron, like I'm not familiar with this, or maybe I'm new to this. So just simply reaching out to manufacturer and getting that type of information. Knock on wood, it's up to this point, I haven't run into a jurisdiction that once we provided this type of data and the explanation of how it works, that it kind of just, yeah, they, like you said, put it in their file and away we go.
Yeah.
Just continue to get that forward. So
Yeah.
One
Just
thing
to
that
further that question, I know you're showing the fully ducted, but in apartment buildings, it's often more beneficial to mount the bath fan in the wall so you don't create a
Mhm.
plenum
Yeah,
in the
yeah,
ceiling, and then mount the ERV, HRV in the wall as well, and not have to build yourself, the upside down bathtub in the ceiling and double sheetrock and all that. Do you have a solution coming for that, or is it available now?
yeah, more to come, Aaron, on that piece. Yeah, so that's obviously as we're starting to see more and more of these codes in that high-rise space,
Mhm.
push or drive the requirement for these types of products. Certainly, again, addressing that problem statement is obviously top of mind for us. And so, short answer is yes. More to come on that piece.
I would love to have EBA be first to know. Like when you're ready to launch that, I want to have you both back
All right.
and talk about that great new product because I think it's needed in the marketplace.
Yeah.
One question we have from the audience is, are these bath fans built to run 24/7 without breaking due to heat, wear and tear, et cetera? And then maybe a follow-on question to that is like, what's the warranty on the great Brown Newtone product?
Yeah, so I believe in pretty much all our fans now. We use, synthetic lubricants and so on. So yeah, they're, um, depending on the model, they can run tens of thousands, 100,000 hours or something. So they're really designed for continuous running.
Yeah.
They're not going to last forever, but they'll last an awful long time. They're designed for that. Um, as far as warranty, I think pretty much all our products have at least a 3-year warranty on them now. But again, they're going to last a lot longer than that. I think back when I used to be the bath fan product manager, and I think we did some studies, and we think our average bath fan was lasting about 20 years out in the field. You sometimes go to someone's older house and you'll see one from the
Yeah,
1950s. It's still running,
yeah. No, it's pretty incredible. And that's kind of that certainty you talked about with the external ratings from HVI and others. But I mean, if you want a quality manufacturer made right here in the great Midwest, you can't beat Brown Newtown. I had one question on your HEPA versus MERV 13 slide, Travis. So when I
Yep.
looked at that, I read it that MERV 13 is equal to HEPA.
Mm,
I know it's two different languages, but I think I had always heard that actually MERV 16 was a
or
little bit more
16.
equivalent to HEPA. So was I reading this chart incorrectly or?
Not necessarily incorrectly, it's the efficiency in which that particle matter is captured. So HEPA is its effectiveness to capture that 99.9% efficient compared to a MERV 13. So while the particle matter size could be captured by MERV 13, it's that next step that HEPA or MERV 16 essentially is that there's a even higher percentage or likelihood that it's going to get captured compared to when you're at a MERV 13 type
Right.
level. So
Got it.
yeah, I can see where you get Aaron, the graphics, yeah, show, hey, everything looks the same,
Yeah.
but yes, there is that additional kind of like, hey, yep, there's a efficiency difference between
Okay.
HEPA and MERV 13. So
Right. I do think an incredible change is the requirement we're seeing, particularly in California,
mhm.
around the MERV 13 at the exterior intake. And I think that's a really smart um, play. But I also love what you're doing with the Overture system and AI of actually being smart enough to take an API from a local weather station or air quality reporting and say, you know what, the outdoor, because I live in Minneapolis. If you go back to the cloud slide where those clouds of smoke have been over the past 2 years. I mean, it's been terrible here in the Midwest. I mean, I would love the upgrade to, where it shuts down based on outside.
Mhm.
But can you just talk a little bit about, I think you guys are really thinking critically about most of the time, 95% of the time, outdoor air is far poorer than, or outdoor air is far better than indoors, but there is 5% of the time where
Sure.
outdoors is worse.
Yep. Yeah, no, and that's exactly why that integration to and there's a number of, weather stations, outdoor APIs, et cetera,
Yeah,
being able to utilize all that data. Because yeah, there's, again, we can make, stroke with a broad brush saying, yep, outdoor air is bad, but there's hyper local events, and that's where that outdoor API, grabbing that data from a very local source, can make that better decision versus just a broad, hey, it's a bad outdoor air day for the state of Minnesota as an example. But the reality is it might be a very local event, and it might be local fires or whatever it might be going on. So yeah, that's where being able to grab all that data and then make a decision based on it is where having this type of overture system interact with our outdoor air devices, you can
yeah,
make those again autonomously. We're not asking the homeowner to go and turn off something. It's we're going to use that outdoor data. Let's make that decision. We've set our thresholds. When that reaches this threshold, not a good time to be bringing outdoor air in. Let's shut it down. Again, we're always going to be looking to see, okay, when have we gotten back to good outdoor air condition? Let's
right.
turn it back on, etc.
I
So,
think it's great. And maybe my final comment is I got to see this at the EBA summit, but the Overture outlet product in the bottom left of this, like, you could take that 50-year-old bath fan that's that Brown Newton that's still running, and you
yeah,
can add that to the outlet, and it now makes it a humidity and motion sensor and kind of makes that old bath fan a heck of a lot smarter. Because you always worry about the occupants, the kids not turning it on, right?
yep, yep, exactly. No, you're absolutely correct. Yeah, I've seen a lot of retrofits because of how simplistic it is to
Yeah,
get basically add on that feature and maintain the exhaust ventilation device you got. So,
it's fantastic.
all
Well,
right.
Travis and Patrick, thank you so much for being here today, and we appreciate all you do for the building science community.
Thank you. And we thank EBA for allowing us to present the opportunity to share this type of information. So thanks again.
Absolutely.
Awesome.